Hello friends and welcome to CEC live lectures. In the ongoing lecture series on extraction of natural products, I started with supercritical fluid extraction in my previous lecture. And in that we discussed about the brief historical development of supercritical fluid extraction as a modern extraction technique and how it became more popular in present times. We also discuss about the basic principle of supercritical fluid extraction, wherein we discuss that how the supercritical nature of the solvent helps in enhancing the overall extraction yield through this technique. That is, whenever a solvent is exposed to conditions above the supercritical temperature and pressure, it has properties of both gases and liquid, which helps in increased diffusivity as well as increased solubility, thereby increasing the overall extraction efficiency. We discuss about the solubility and selectivity of a solvent in supercritical fluid extraction. What are the components or what are the parameters that can affect the solubility and selectivity of the solvent? We also discuss about the properties of supercritical fluids with respect to liquid and gas. As I told you that a supercritical fluid has properties somewhat between liquid and gas in terms of its viscosity, whether it's a dynamic viscosity or kinematic viscosity, or its diffusion coefficient or thermal conductivity. So all these properties, all these parameters, they of a supercritical fluid lie somewhat between liquids and gases, and therefore they help in enhancing the overall extraction efficiency or yield of a process. Then we discussed various advantages of carbon dioxide, which make carbon dioxide as solvent of choice in supercritical fluid extraction technique or processes. And these advantages were that it's non-toxic, it's non-inflammable, and it is readily available, cost is low, you can get carbon dioxide of high purity. Then since it's a gas, the solvent residue in the final products are negligible or almost absent, and so on and so forth. Then we also discuss certain disadvantages of carbon dioxide in supercritical fluid extraction, like the polarity of carbon dioxide is towards lower side, and therefore the constituents which are highly polar or towards higher polarity, they are insoluble in carbon dioxide. And to overcome such disadvantages, we use certain co-solvents which are also known as entrainers to solubilize the constituents which are highly polar into carbon dioxide. So friends, in continuation with my previous lecture, today I'll start with the process of supercritical fluid extraction. What are the steps that are involved, and on the basis of step, what are the different extraction modes of supercritical extraction process. So this process has broadly two major steps. First one is the extraction, wherein the desired components are extracted from the matrix or the feed material. And second one is the separation, wherein the extracted components are separated from the solvent. Now, extraction can be of two types depending upon the end result or the end product. And the first one is wherein the feed material or the matrix, plant matrix, is separated from the non-required constituent. Say for example, we have come across a term decaffeinated tea or coffee, from which caffeine has been removed. So this type of example falls under this category, wherein we separate the plant material from caffeine as a non-desired product. And the second type of extraction is the general extraction of the secondary metabolites which we require. And these secondary metabolites or the phytoconstituents which we extract out from the matrix are utilized for different purposes. So the second step is the separation. Now, as I told you, this step involves the separation of extract from the solvent, and this can be achieved by two strategies. First one is by modifying the thermodynamic properties of the supercritical fluid or the solvent which we have used in this process. And as we discussed that carbon dioxide is the solvent of choice for supercritical fluid extraction, and you will come across majority of the literature will show that carbon dioxide is largely used as the solvent. So as we discussed when we in the principle of supercritical fluid extraction, that whenever carbon dioxide is exposed to the temperature and pressure conditions above the supercritical values or the critical values, that under those conditions carbon dioxide act as a liquid as well as gas. So it has both diffusivity of a gas and solubility of a solvent. But if you slightly change or decrease the pressure and temperature, the properties of carbon dioxide altogether get changed and it start coming back to its original form, that is the gaseous form, wherein the solubility power of carbon dioxide also decreases. And this principle is exploited during the separation process, wherein we modify the temperature and pressure conditions in comparison to the conditions which were there in the extraction vessel, and as soon as the pressure and temperature conditions are varied and by and large pressure is released, pressure is decreased and temperature is also decreased, this causes the conversion of carbon dioxide from its supercritical nature to back to its gaseous form, and as soon as it get back to its gaseous form, the solubility of the components decreases and they get separated from the solvent, that is carbon dioxide. Separation can also be achieved by using certain external agents, and these can be adsorbing agents or absorbing agents. Now, as you can see in this image, there are 4 different images. The first group, or which comprises of the top 2 images, it is largely the separation. These figures depict largely the separation done by modifying the thermodynamic of the supercritical fluid. So in the first image, the pressure is reduced. So as I told you that as soon as the pressure is reduced, carbon dioxide get converted into gaseous form, where the solubility power of carbon dioxide decreases, and whatever constituent it has extracted from the plant matrix, they get separated into a separator. And once they get separated from the carbon dioxide gets converted into gas, and it exits from the separator from the top side, and it is circulated back into the extractor. Whereas the constituents which are separated, they are collected into a collection vessel from the bottom of the separator. In the second image of the first group, you will see the setup wherein the temperature conditions are varied. It has been observed, now when temperature conditions are to be varied, there can be 2 scenarios. First is you decrease the temperature and solubility decreases, and second is you increase the temperature further, which will again help in decreasing the solubility. Though majority of our examples, you will see that when you decrease the temperature, solubility decreases, but there are certain exceptions wherein by increasing the temperature, solubility decreases. So whatever the case may be, accordingly we alter the temperature conditions, and again when the temperature conditions are altered, there is alteration in the solubilizing power of the solvent, and the constituent as well as the solvent get separated in a separator, and the solvent which gets converted into gaseous form, it is again recirculated back into the extractor through heat exchanger by maintaining the temperature which is required in the extractor, and then the extract is separated from the bottom side of the separator. In the second group of images, wherein we use certain external agents to separate the extracted constituent from the solvent, and first one is by using the adsorption mechanism, wherein we use certain specified material to adsorb the extracted constituent onto that material, and from there we can separate that adsorbing material or the material which has constituents adsorbed on it. But the major problem with this technique is the final yield of the constituent is low in comparison to the above 2 techniques. This is largely because it's very difficult sometimes to separate complete or the entire quantity of the constituents that have been adsorbed on the material, and therefore sometimes the yield decreases in comparison to the yield that is obtained by modifying the thermodynamic conditions. In order to overcome this loss of yield, another technique was developed wherein absorption of the constituent was done onto a second external agent, and this is largely done with the help of a viscous liquid which moves in a counter current direction of that of the extract. Now, when that viscous liquid moves in a counter current direction of the extract, the constituents which are more soluble in that viscous liquid, they get absorbed into that particular liquid, and the gas is, or the supercritical solvent is separated. So these are the four major scenarios, that is how separation occurs once the extraction in supercritical fluid is over. Now, supercritical fluid extraction can also be carried out in a fractional manner, which we call it as fractional extraction process. Now, many times we require extraction of different type of constituents based on their polarity. So, in order to extract different constituents on the basis of their polarity, we use fractional extraction process. And this can largely be done by changing the polarity of the supercritical fluid solvent. And we know that polarity can either be changed by altering the thermodynamics of the system, or by incorporating certain co-solvents or entrainers which help in improving the polarity of the supercritical fluid solvent, which is carbon dioxide largely. So when you have to change the polarity by altering the thermodynamics, in such scenario, during the first step, we use low fluid density of the solvent, supercritical solvent, wherein the pressure and temperature conditions are lower. In such cases, this type of solvent is suitable for extracting out non-polar constituents, and such constituents will be easily get solubilized in the low fluid density. So once step 1 of extracting the non-polar solvent is complete, then the remaining mark is then treated with the solvent with high fluid density, that is, we further increase the pressure and temperature conditions in order to increase the density of the supercritical fluid, which help in solubilizing more polar components. As I told you, the second scenario is by using entrainers. So in such scenario, we first extract the plant matrix by normal supercritical fluid solvent, which extract out most of the non-polar compounds. Then the mark is exposed to the supercritical solvent along with the entrainer or the co-solvents, and as we will discuss ahead, these co-solvents or entrainers most commonly used examples are ethanol, water and methanol. And methanol being toxic is largely avoided when the extraction is being carried out for edible purposes or in food industry. So when the supercritical fluid, which is carbon dioxide, is mixed with co-solvent, its solubilizing power changes altogether under supercritical conditions, and now it is more suitable for extracting the polar components. So this is how we can go for the fractional extraction process using supercritical fluid technique. Now another technique by which we can go for fractional extraction process is by sequential depressurization. So you can see the figure, the extract which is first extracted by using normal supercritical fluid, it will extract both non-polar constituent, and we can also introduce co-solvent at the very first stage, so that during this extraction process we can extract out non-polar as well as polar constituent. So once the extraction is complete, that extract is then subjected to the change in the pressure conditions. So first slightly depressurization is done, and due to this polar constituent, they get insoluble in the extract, because as you depressurize the extract, the properties of carbon dioxide changes and it will become the solubilizing power for polar constituent will decrease. As a result, polar constituent will separate out. Then in the second step of depressurization, the pressure on carbon dioxide is further reduced, or on the extract is further reduced, which further decreases the solubilizing power of carbon dioxide, and thereby medium polar constituent get separated. And in the final step, further it is depressurized in order to get the pure fraction containing the non-polar constituent. So this is another way by which we can go for the fractional extraction process. Now we move on to the extraction setup for the solid samples. Now there are different steps that are involved for the solid samples. So once the sample is loaded in the extraction vessel, the second step involves the introduction of solvent into the extraction chamber. Now before we introduce the solvent into the extraction chamber, the solvent has to be maintained at the pressure and temperature conditions that are required in the extraction vessel. So once the solvent is maintained at the pressure and temperature conditions required in the extraction vessel, that is the pressure and temperature conditions above the critical values, it is introduced into the extraction vessel and the solvent is mixed with the matrix there. The mixture of solvent and the feed material is maintained at the required temperature and pressure conditions, that is above the supercritical values, for specified period of time. And once this time is over, extraction is complete, the extraction vessel is slightly depressurized so that the solvent which has extract or the constituent solubilized in it, it can exit the extraction vessel from the top side. So once it exits from the top side, this mixture is introduced into the separator where further depressurization is exposed and the constituent gets separated from the carbon dioxide. Now once this process is going on of separation, the extraction vessel is opened, because now the extraction vessel is completely cut off with the help of valves from the separator. So once the separation is going on in a separator, the extraction vessel is opened and it is unloaded by the spent material. So whatever mark or the spent material is there in the extraction vessel, it is removed and the fresh material is loaded. And in the meantime, once the fresh material is loaded, the extraction vessel is sealed. So in the meantime, the depressurization which is happening in the separator, it causes the removal or the separation of the supercritical solvent, that is carbon dioxide, and the constituents that have been extracted. So the carbon dioxide is released from the separator and it is circulated back into the extraction vessel for the extraction of the second batch, and the extractor is then separated from the extract or the constituent are removed from the separator. So as you can see in this flow diagram, this is nothing but the flow diagram representation of a supercritical fluid process. You can see there is a vessel which is labeled as 1. This vessel is a storage vessel for the entrainer or the co-solvent, which are pumped with the help of pump into the heat exchanger, which is labeled as 5. Now carbon dioxide along with entrainer, they are entered into the vessel number 5, which is heat exchanger, wherein they are maintained at the pressure and temperature conditions that are required in the extraction vessel. So this preheated and pre-pressurized mixture of solvent and the co-solvent, they are introduced into the extraction chambers, which are labeled by 2. And once the solvent mixture of solvent and the co-solvent enter into the extraction chamber, they are maintained at the required temperature and pressure conditions for specified period of time. After that, they are depressurized and the extract, it exits the extraction vessel and it enters into the separator. Now in the separator, depressurization occur, and as I told you that the constituent gets separated from the gas, which are collected into the container number 6, which is the product container or the product tank, and the carbon dioxide is again exit from the separator and it enters into the heat exchanger, where it is further cooled down and is stored back into the CO2 container that is labeled with the number 7 and 8. So again this carbon dioxide is recirculated back through the heat exchanger into the extraction vessel, and the whole process continues. So this is how the supercritical fluid extraction process takes place. But when we talk about the industrial scenario, because a lot of cost is involved in an industrial setup and they cannot afford to stop the process to unload the spent material and fresh loading of the material into the extraction chambers and then again start up the process. So continuity of the feed as well as continuity in removal of the spent material is of utmost requirement in an industrial setup. So in order to achieve that continuous feed and discharging of the material, the extraction vessels are arranged in a series. So as you can see in this figure, 4 extraction vessels are arranged in a series, and once the extraction is completed in the vessel number 1, the extract is exited from that particular extraction vessel. Carbon dioxide is separated from the extract. It is recirculated back into the second extraction chamber. The extraction started in the second vessel. In the meantime, first vessel is emptied and it is reloaded. In the meantime, second extraction is complete, then it enters into the third, then into the fourth, and then it's again circulated back into the first vessel. So this is how the continuity in the extraction is achieved in an industrial setup of supercritical fluid process. Now this is, in this image you can see an industrial commercial setup for a supercritical fluid extractor, wherein you can see around 5 extraction vessels are arranged in the series as we have discussed in this image. You can see the 5 extractors are placed in the series, and the extraction is continued in all the 5 extractors in one go, and simultaneously the spent material is removed from the vessel, fresh material is charged in the vessels, carbon dioxide is again recirculated. By achieving this continuity of removal and loading of the sample, lot of money is saved in this industrial process. One. Second, cost factor also improves when the carbon dioxide is again and again recirculated in these 5 extraction vessels. So such kind of arrangement help industry in reducing the cost of overall extraction process. Now these kind of extraction setups are largely for the solid material, where we have the feed material in the form of solid. So friends, till now we have discussed the instrumentation or the process that is largely related to the solid material. So in the coming lecture I will be discussing about when you have a sample which is liquid in nature, so how you can handle that liquid sample, what are the changes in the extractors that are made to handle the liquid sample. Thank you.